All right, so today we're going to talk about exponential functions. First, let's go ahead and review other functions that we've already talked about. Types of functions that we've heard about or that are most familiar are linear functions. Now, what are some characteristics that we know about linear functions? Well, we do know that they have a slope, most people say. But there's a word that I want with slope that I want to talk about that is specific to linear functions. Okay, what is it? It's constant. Slopes in linear functions are constant. Now, typical graphs that you're used to seeing in terms of linear functions are something that looks like this. Maybe that's y is equal to x. And then we're also used to seeing things that are horizontal lines, where they have a constant zero slope. We're also used to seeing lines that go directly up and down. Now, we know that this is considered an undefined slope, and it also does not pass the vertical line test. We've also talked about things like quadratic functions, okay? But today we are going to go ahead and get into exponential functions. Now, by this point, you would have gone ahead and you already have your vocab done and written down for the first 5 minutes of class. So, exponential equations. What is an exponential function? An exponential function is just a function of the form f of x is equal to b to the x, where b is your base and x is your exponent. Now, you're used to seeing things like quadratic functions, and quadratic functions actually have things or exponents that are x squared, so that's x to the 2, or used to seeing trinomials where you have x to the 3, so it's x cubed, okay? But in this case, x is actually our exponent instead. Another thing we're going to talk about is compound interest. So this is interest accumulated on some initial principal or investment, and it also accumulates on the initial interest from an earlier time period. Okay? We'll talk a little bit more about that later in the lesson, but what I want you to make sure you write down is this formula. This formula is going to be very, very important to talk about, and you are going to have to know for your unit test. In order to be able to start talking about exponential functions, I want to show you a little bit of a video, and it has to deal with how do you make a fool out of a king, okay? So let me go ahead and introduce that to you first.
This is an old story, but it reminds us of the surprises we can get when even a small number like 2 is multiplied by itself many times. King Shahram of India was so pleased when his Grand Vizier Sisabendar presented him with a game of chess that he asked Bendar to name his own reward. The request was so modest that the happy king immediately complied. What the Grand Vizier had asked was this: that 1 grain of wheat be placed on the first square of the chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth.
All right. So let's go ahead and go back to our PowerPoint. Remember hearing that the peasant's request, okay, so essentially just to sum it up, what happened? Peasant brought a king a chessboard, and it was this great game, and the king was so pumped about it. But what happened was he said, listen, I'll go ahead and let you name your prize, okay, or your payment for this wonderful game, all right? Now, the peasant was no fool in the sense that he knew that he could get something truly wonderful out of this. So what did he say? He said that he wanted 1 grain of rice on the first, doesn't seem like much. He wanted 2 on the second. He wanted 4 on the third, and he wanted 8 on the fifth, 8 on the fourth, and then 16 on the fifth. Now, what I want you to do, go ahead and do in your groups, is I want you to go ahead and talk about what is it that this pattern is holding. What is going on each and every time that the peasant is asking for more and more rice on each square. Okay, so go ahead and talk about that. And once you've done that, go ahead and fill in the first 2 rows of this entire square once you've found the pattern. Okay. Now, by this time you would have gone ahead and you've talked to your groups and you would have gone ahead and found your pattern. Most people would be saying right now, it's multiplying by 2 each and every time, right? Because 2 times 1 is 2, 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16. And you would have got numbers like 32, 64, 128, 256, 512, 1028, 2048. Hey, I love that game. 4096, 8192, 16,384, and then 32,768. Now, by that time, I'm sure you probably pulled out your calculators to get that done, and that's totally fine in my class in certain points. Now, in this case, what would happen if we went, say, to the third row, like it says in your packet? Well, obviously, this would have become very large numbers to the point where we may not even be able to fit it inside the square because we'd had so many digits. Okay? So what does this all mean? Well, what I want you to go ahead and do is, in your packets, I want you to go ahead and let's use our X and Y chart, okay? And what we're going to do is we're going to call the first chess square, we're going to call that 0, X is equal to 0. And I want you to go ahead and put in your Y values, okay? So the amount of rice on your Ys, as you can see from your graph that I've made for you, your Cartesian graph, that our X-axis is going to be our chess squares and our Y-axis is going to be our grains of rice. So the numbers you would have put into here are 1, 2, 4, 8, 16, 32, 64, and 128. Now what I'd like you to go ahead and do in your groups is go ahead and graph this on our Cartesian plane. Once you graph it on your Cartesian plane, you would have gotten something like this. Now it doesn't have to be exactly because again we don't have a hash for each and every one of our numbers. But as long as you have a great approximation, then you can have essentially the same exact graph that I have. Now of course through any graph we always draw a smooth curve. So as you can see, this is the pattern, or this is what our peasant was asking for from the king. Now this is what we call exponential growth. Exponential growth is again something where it starts out really slow and then all of a sudden it just seems like it takes off, kind of like you saw on your chessboard. Man, it just seemed like it was really small, and then before we knew it, it was so large. If we'd had to fill out that entire chessboard with stuff, what would happen? Let's go ahead and go back to our peasant king and let's see what happened.
Square and so on, doubling the amount of wheat on each succeeding square until all 64 squares were accounted for. When the king's steward had gotten to the 17th square, the table was well filled. By the 26th square, the chamber held considerable wheat, and the nervous king ordered the steward to speed up the count. When 42 squares were accounted for, the palace itself was swamped. Now fit to be tied, King Sharam learns from the court mathematician that had the process continued, the wheat required would have covered all India to a depth of over 50 feet.
So, going back to our PowerPoint, what I want to go ahead and do now is what is the function of our graph that we actually have. So we have, just using our information, we made an X and Y chart, we went ahead and we graphed some points and we drew a smooth curve. But is there an actual function that can represent this? Here's some questions I want you to go ahead and ask yourself. First, what tells us to repeat the multiplication of the same number? Go ahead and ask that to your partner right now. So what you would have come up with is what is it that tells us to repeat the multiplication of the same number? Well, 2 times 2, how do we represent that? We represent that as 2 squared, which is equal to 4. How can we represent 2 times 2 times 2 3 different times? That's 2 cubed, so that is equal to 8. So as you can see, those are all numbers from our chessboard or also from our Cartesian graph. Okay? So what's the next number though? What is the value of anything raised to the power of 0? Okay? What is the number? What is anything raised to the power of 0? Well, most of you remember seeing this. If you have, say, 2 to the 1 over 2 to the 1, we know because of division properties that this is actually just equal to 1. Right? The numerator and the denominator are the exact same thing. Your fraction is just 1. However, also because we also know exponent properties from the previous unit, we know that we can take 2 to the 1 and subtract off another 1 from our exponent. And then therefore 1 minus 1 is equal to 0. Therefore 2 to 0 must equal 1. Okay? So what does that mean? What is our actual function of this graph? What would it be if 2 to this, if it's 1 at 0, if it's 2 at 1, and then it's 4 at 2, and then it's 8 at 3. So what is our pattern? Well, what you come up with is you have 2 to the x. That must mean that every time that we're plugging in for x, right, if we plug in 0 here, what do we get? We get 1. What happens when we plug in 1? We get 2. If we plug in 2, we get 4. 3, we get 8. 4 we get 16, 5 we get 32, and so on and so forth. Which, if you were to go back to our, if we were to go back to our x and y chart, that is exactly the same numbers that we had. So this is just a little bit of a introduction into what are exponential functions and what do they look like. They start off slow, and then all of a sudden they just take off, it seems. Kind of be nice if that was our bank accounts, right? Now, in this case, what we're going to do is we're going to go ahead and go into how do we solve exponential equations.